All right, let's get into the fat. We're getting in them lipids. We got, um, a little outline here. Functions and types of lipids, what we're going to go into first. Then we will talk about the specific types here. And these are actually our types kind of listed out here. So let's talk a little bit about lipids in general and what they're doing, for living beings and for the cell. I mean, the first thing that they're kind of doing, so functions of lipids is their energy storage. Functions of lipids. They're an energy source, and like I got a nice little. Whoops, that's not what I wanted. Get out of my face! I didn't ask for you. Get out of here. I'm asking for this guy. You get in here. I just wanted to start off with this. Actually, I kind of messed up. We got our little lipids right here. It's an avocado. It's mostly made out of lipids. So that we eat it and spread around that pit. Plants are tricking us into making more of them. So they're energy storage, especially long term, like we store fat in our body. Structure of cells. We could not have cells without lipids, and we'll talk about how that works. So they actually build the cells in themselves. Also used in cell signaling / communication. Dude, my brain is off. And they protect us. They give us cushioning. So like on the heels of our feet, for example, we got little layers of lipids so that we don't just be rubbing our bones on our skins and our muscles. So they provide us with some protection. All right, so now let's go through the different types of lipids. We'll just do that in blue. So some different types would be triglycerides. These are mostly going to be energy sources and storage. Very highly calorically dense, and you'll see why. Then we've got our phospholipids. And these actually come in three different, triglycerides come in two different varieties. They come in oils, which is plant-based, and they come in fats, which is animal-based. So oils, examples would be cooking oils, like vegetable oil, olive oil, avocado oil, cooking oils. And fats would be like butter / lard, for example. These are from animals. Pretty cool. Animals, and these are from plants. Okay, so those are triglycerides. Then we have phospholipids. Do those in this blue. Phospholipids. They're a lipid with a phosphate. These make up our cell membrane. These encase cells. They separate cells from the outside world. Then we've got our steroids. Need a different color, actually. Sorry. We got our steroids, which are hormones / signaling molecules. So these allow cells to communicate with each other. And then we got waxes. We got some waxes. And these are, we make them in our ears, like earwax. Blueberries and other plant material has it. So like outside of plants. These provide protection, prevent water loss. So, functions of lipids, energy storage, structure cells. How about a major property of lipids? Major property property of lipids is they are hydrophobic or non-polar. We go all the way back to water. Bam. Remember, water has this special property where the electrons like to spend most of the time with oxygen. So oxygen's a little bit negative and the hydrogens are a little bit positive. This makes water polar or sticky. So they have this positive or this partial charge across the molecule. Another word for this is it's a polar molecule. Okay? Has a slight charge. Slight charge. Slight charge. Fats don't have that. They are mostly made out of carbon and hydrogen, and carbon doesn't pull the electrons as much. So, lipids are hydrophobic. So this means that water and lipids don't mix well. They don't mix well together. And you can do this little experiment in your kitchen with a little bit of butter or a little bit of oil and a little bit of water. You will see that they do not mix very well. All right, so let's start with triglycerides. And a triglyceride, I'm just going to give you guys like the real basics. Like at the top of a triglyceride, there's something that looks kind of like this. And I don't really care that you know the biochemistry of it. It's a glycerol molecule. And then there's ester bonds. And then we've got these, but I don't really care that you know that, like I just said. And we've got these things coming off of them. And guess what? It's called a triglyceride. This is where the glycer comes from. This is actually a glycerol. This would be a glycerol molecule. At the top there, and then tri, meaning it's got three of something, and it's got three little legs coming off the bottom of it. No, what is going on there? I want this. I want to kind of zoom way out because I want them to be kind of big. It's got 1, 2, that's maybe a little too big. It's got 1, 2, 3. Triglyceride. See where we get the tri from? 3 legs coming off of that. And each one of these legs is a hydrocarbon. So it's this carbon backbone. So each leg is a hydrocarbon. It's made out of carbon and hydrogens. If we draw it like the carbon skeleton, it would look something like this. You remember that? So we could draw these out all like that. I'm not gonna do that, but we can. All right, and these things are packed with energy. So this is just a hydrocarbon, just like gasoline or sugar, and it's got 3 of them. So we could have something like an enzyme come in here. We could have something like an enzyme come in here and just chew on the end of this and make a bunch of energy off of it. Gobble down. And we could get energy out of that. And that's why fats have a bunch of energy. So each one of these is like, it's almost like you think of it as a big, long, straight sugar. Okay? All right. Now, a couple things I want you to know. All right, remember we had 2 different types of triglycerides. So we got one here, and I'm going to just recopy this and put it down here. We also have triglycerides that look something like this. Very similar. Very, very similar. Not too different. But there's one major difference. The way the legs are. So in this one, up here we got straight legs. Straight legs. On this triglyceride. Down here, We got bent legs. We got kinky legs. We got kinky legs. They're all bent. They are all bent. Bent out of shape. Okay, pretty interesting. What does this mean? What does this matter? Who cares? No one gives a crap. Tori, you're boring the crap out of me with your nonsense. Who cares about these kinky legs? All right, well, in that top one, we got all these straight legs, right? They can stack up nice and neatly. You get a bunch of these molecules. You don't necessarily have to draw this. It's okay. I'm going to make them a little smaller. Boom. 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 Oh, yeah, they love this. Yep, and we'll put some there. Oops. All right. Oh, yeah, they love this. This is like, they're just like, you know, all cuddly. And they're all just like jammed here together. They're jamming out. They're vibing. Woo! Okay. They are very cool hanging out with each other. Whereas these guys, I mean, look at this. They can't even like, how am I gonna, okay, they can't even get close. They gotta kind of be like far away. Maybe that one fits in there. All right. Maybe this one here. All right. Okay. See what I'm going for there? These ones can fit tightly together. These ones are all they kind of got to be more spread out, a little more loosey-goosey. This makes a huge difference in their properties. So this would be animal fat, like butter or lard. This down here would be oils, plant oils. So these are solid at room temp. Now you know why butter is solid at room temperature. Isn't that nifty? It's because of this biochemical difference. The kinky versus straight legs. And animals are a little, you know, they're a little more buttoned up than plants. Plants are a little goofy, a little strange. And they got kinky legs. Oils are liquid at room temp. You know, it's pretty cool. I still think that's pretty awesome. All right. And the reason why that is I'm sure you've heard these terms. These here, their hydrocarbon skeleton, like this, is saturated with carbons. So it's a saturated fat. That's what that means. Saturated fat means that the carbons are saturated with hydrogen. Pretty nifty. So if we, you know, kind of do this whole little process and label all of these with our hydrogens, like so, every one of these carbons is going to be bound to 2 hydrogens. That's what saturated fat means. Okay. And this of course would continue on. I'm not going to draw it out, but that would continue on. And then this one would actually have 3. Okay, so it's saturated. So the legs are straight. Our body can digest these very easily. Our body can digest these very easily. Pretty nifty. A little health advice here. Butter is actually technically healthier than a lot of oils. Or margarine. Margarine is made out of plant oils, usually. Okay, so what's going on with the plant oils? Liquid at room temp. So these are mostly from butter or lard. This would be plant oils. Plant oils. Butter or lard comes from animals. This is animal based. Okay. Liquid at room temp. All right, so let's redraw our hydrocarbon skeleton so we can see the differences here. So if I draw one of these legs, it's going to be a little different than what we've seen before. And there's actually two kind of differences that it can be. So we can have, let me draw these in black. So we can have a leg that looks something like this. And one of these carbons, this would still be straight, actually has a double bond. And then we can have another one, let's say that is something like this. Pretty nifty. And this here would be a double bond. All right. So double bonds just means that the carbon is bound to itself twice. We could draw in our little hydrogens here. Draw in our oops, not G, no, hydrogen, hydrogen. This would keep going. Hydrogen, hydrogen. This one's only going to have one hydrogen because it's got this double bond. So this carbon would be bound to 1, 2, 3, 4 things. Same thing for this one. It's only going to have one hydrogen. And so it's not a saturated fat because it's not saturated with hydrogens. See what we're talking about here? Okay. Continue that out. Beautiful. And then this one going to have, it's 3. All right. All right, same thing for here. This would continue out. We'd have our hydrogen, 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 and then we're only going to have one hydrogen, because these carbons are double bonded to each other. So this carbon here is bound to 1, 2, 3, 4 things. Hydrogen, hydrogen, and at the end here is going to have, again, 3. Okay? So we can have these different orientations for double bonds. So with the double bond, the carbon can go across, it can translocate, it can travel. This is a trans fat. It's a trans double bond. Ooh. To go across, to transfer, trans, I don't want cap lock, trans double bond. This is a trans fat. Trans fat. This over here, nope, not what I want. Move these guys. This over here, the bond, the carbons are on the same side. It is cis. It is the same cis bond. It's a cis bond. This is a cis fat. Okay, you don't often hear that, but you will often hear trans fat. Cis fats are okay, actually. A cis unsaturated fat. We can digest these. No problem. But a trans fat, bruh. We lack the enzyme to digest trans fats. So trans fats are very unhealthy for humans. So check your nutrition labels for trans fats, and they don't always have to report them. It has to be over 0.5 gram. And avoid them. Pretty nifty. Okay, that's a lot on triglycerides. So you now know why butter and oil are either solid or liquid at room temperature. Pretty cool. You also now know what a saturated fat is. It's actually totally fine for you. People talk about them as being something bad, but a saturated fat is totally cool. Body can digest that very easily. It's trans unsaturated fats. This is unsaturated because it's not saturated fully with hydrogens. A cis unsaturated fat, no big deal for you, but a trans unsaturated fat can give you some health problems. Okay, now let's talk about phospholipids. Very similar to triglycerides. So this was triglycerides. triglycerides. Now let's talk about phospholipids. Okay? Phospholipids. That's a big old fancy word, really. Phospholipids, main difference between triglycerides and phospholipids is phospholipids have a little polar part to them. Phospho, this means phosphate group, but it's very similar to a triglyceride otherwise. So we'll go through this one pretty quick. So a phospholipid has a little head like this. It kind of looks like a little person with no body. This is actually kind of how I drew people when I was younger. And there's different types of phospholipids, but in general, this is what they look like. They will have two tails, like so. Like that, boom. That's a phospholipid. So these parts here are a hydrocarbon tail. They are made out of hydrogen and carbon, and so then they are hydrophobic, which means they don't like water. They don't like water. They don't want to be with water. They're just like any other lipid. They don't like water. No thanks. Whereas this polar head, it's mostly made out of, the polar head is made out of phosphorus and oxygen. It's a lot of phosphorus and oxygen. So it's kind of negative up here. Because they attract electrons when they're part of a molecule. Electrons like to spend time with phosphorus and oxygen. Okay, if we go back just to this water molecule again and just look at that, the reason why oxygen and phosphorus is even more what's called electronegative is because these electrons want to spend more time with oxygen than they do with hydrogen. And so that makes oxygen slightly negative. So this phospholipid, it's got two different personalities. It's got a polar side. So it's got a polar side, and a non-polar side. Amphipathic is the term for that. So like a two-sided molecule is called amphipathic. I think is how you spell it. It's kind of a big sciencey word, but it's got two different kind of properties to it, a polar side and a non-polar side. So this side is a negative charge. Okay, and this side is just neutral. So what this results in is if you put these in water, they'll arrange themselves in a very special way. So I'll just kind of draw this out quickly. Naturally, they will just spontaneously do this all on their own. Let me draw these out. We got our little phospholipid there. So you add these to water and they will spontaneously do this. It's pretty cool. Like so. And we just extend this out. And then we gotta do this down on the bottom here. Boop, boop, boop. And we gotta add in our little feetsies. Like so. So you add phospholipids to water and they will automatically do this. And so then on the outside here, and I'll talk more about this kind of in the future as well when we talk about cells. So on the outside here, we will have a bunch of water molecules. So water will be on this side and water will be on this side. And then inside here, we've got, actually let me make the water a different color. Here we've got, we'll have water, sorry, this is a little confusing. We'll have our water molecules all out here. Water, and water is polar. So water is polar. It loves to hang with the polar heads of a phospholipid. And inside here, crammed in this little phospholipid sandwich, these hydrophobic tails love to hang out with each other and exclude water. So based on the amphipathic chemical properties of a phospholipid, you essentially create a cell membrane. So what this results in is if I kind of just extend this out, they will actually form a sphere like this all the way around with one layer and then a second layer like that. And inside of here, we will have all these, I'm not going to draw them all in, but we'll have all these little tails. Right? This will be all full. This is so trash, but you get what I'm going for. This is all full of hydrophobic tails in here. This is so bad. I'm just going to keep making it worse. So the hydrophobic tails are in here. Hydrophobic tails are happy in here. And the polar heads are happy interacting with polar water. Because again, this is all water, and this is all water. Right? This thing is essentially a cell membrane. Pretty cool. You can also form smaller versions of this depending on the phospholipid that you use. You could form something called a micelle, which is a single layer, something like this, a single layer, and the tails are all pointing inside like this. And this is a great little pocket for hydrophobic things like dirt. Like we'll have a little pocket of dirt. So this would be a micelle. A micelle. It's great for removing dirt. This is also how soaps work. There are also little lipids. If you've ever used a micellar cleanser, that's what's going on, is you have this kind of amphipathic molecule. That's how detergents work as well, that then encapsulate a little dirt particle and allow you to rinse it away. And that's all just based on the chemistry of phospholipids. Okay. All right, 2 more little things in lipids, but these will be fast, and I'm not going to spend too much time on them. So that was phospholipids, steroids, and waxes. So steroids are ring-based signaling molecules. So examples are cholesterol, testosterone, and estrogen. So I'm sure we've heard of all of these actually probably before. Testosterone. So these are our sex hormones. These are our sex hormones. They masculinize or feminize a body. And cholesterol has a lot of different functions, but is actually also very important in our membrane. Very important for many functions, but specifically for changing the fluidity of cell membranes. So they can make cell membranes themselves either more or less fluid. Cell membranes. Pretty cool. Okay. All right. I'll draw out testosterone, I guess. We'll just draw out testosterone. Just to give you an example of what one of these looks like. So just one example, and that's kind of it. Since these are lipids, they can easily get through the membrane. That's why they make great signaling molecules, because they're a lipid. They can get right through that hydrophobic tail. So testosterone looks something like this. It's got a little six-sided structure here, a little carbon ring. That is kind of trash, the way I drew that. Let me actually restart that, sorry. Did not draw that very good. So I want to draw it like so. That's better. That's still not perfect, but it's better. We got another little carbon coming up there. We got another one of these bad boys. Something like that. We got another little 6-carbon ring coming off like this. This should kind of come down like that and like so. And then we got a little 5-carbon, just like a little house looking guy. And we got a little carbon coming up here and another little thing coming up there. This would be a double bond. This would also be a double bond coming over here. So this is all just hydrocarbon, ring-like structures of a hydrocarbon. Okay, so since this is all hydrophobic, it can easily pass through cell membranes. We'll talk about different types of diffusion through membranes, but this thing can just go like a ghost, just slide right through. Like a ghost, it can just slide right through membranes. Pretty cool. All right, and then last but not least, we got waxes. And waxes, I'll do those in, I don't even know, orange. That makes sense for wax, like earwax. So waxes. So examples of these are, they're solid at room temp. Earwax. Plant cuticle. And something like beeswax. Little Burt's Bees right here. Put this on my lips. It helps prevent dehydration. Pretty nifty. These guys, they're just a big old long hydrocarbon, and they're kind of connected in the middle with something called an ester bond, which just has some oxygens. So I'm just going to kind of draw like a little square here in the center, something like this, which kind of has some oxygens. And then coming off either end of it, it's just like a big old long hydrocarbon. And that's really all I cared that you know. Let's make that a little prettier. Well, we don't have to be too specific, too detailed. They're getting this carbon scale getting longer as I'm going, but you get the idea. So this is just a big, long hydrophobic molecule. So you can see how if you just put a bunch of these like on, for example, your skin, how this could help prevent you from dehydrating. So it's a big, long hydrophobic molecule. Useful for preventing dehydration. So, on my lips, for example, I just put that Burt's Bees. So if, my lips were down here and I basically make like a little wax blanket for it, to kind of keep all my water in. So if this was all my water in my lips down here, it can't get up through this wax if it dries. It's going to be thwarted. Water won't be able to escape my lips. So you see why this is useful for plants. Like, they don't want water just leaking out of their whole body. They want it leaking out in very specific areas that they can control and regulate. Yeah, so we use this for all kinds of functions. We also use it as a fuel source in our candles, right? You burn a candle, that's made out of a wax. It's a bunch of hydrocarbons. You add a little bit of flame to it, you can create combustion, which will chew these big long fuel sources away, turn them into CO2 and water. Remember that a hydrocarbon is just a fuel source. So even the biological hydrocarbons are great sources for burning, creating combustion. Okay, that was also long. Whatever, deal with it. You're paying for this. All right, I'll see you guys in the next one. We're going to be talking about proteins.